Hey guys, this is Mr. Ainsworth, and we're going to get into a little bit of proving closure activity here to get you ready for activity 1C2. Yes, we're going to learn how to prove algebraically. All right, so let me pose a problem. We'll get right into it, and we'll do a little arithmetic here and kind of make sense out of it. All right, so let's take a look at this problem here. All right, so let me pose a problem. So let's take this set I. This little symbol means set right here. And let's say that we're going to take all the numbers of the form. So numbers of the form. Okay, 5n plus 1. So 5n plus 1 here, where n is a natural number. N is a natural number. Okay, you have to know what natural means. Okay, so it's a natural number. And is this set, okay, which we call I, just for namesake, I guess. All right, is this set right here closed, all right, under multiplication, under the operation of multiplication? Now we can explore any operation we want. I pick multiplication. So is this set where we take a look at the numbers of the form 5 times a natural plus 1, all right, is it closed under multiplication, which means if we take any two numbers in the set and multiply them together, do we get a number in the same form? That's what closure is all about. All right, so let's get a little idea what this set looks like. All right, so natural numbers. So natural n, obviously the natural numbers start at 1, and then 2, and then 3, 4, and so on. Those are the naturals. To infinity, okay, and beyond, as Buzz Lightyear used to say. All right. Okay, and so let's get a feel of what this is like. And this is what mathematicians do. If you can't visualize these numbers, then you start calculating so you get a feel of what they look like. All right, so the first number, when n is 1, that's 5 times 1 plus 1. Well, 5 plus 1 is 6. When n is 2, all right, that's 5 times 2 plus 6. Excuse me, plus 1, which is 11, right? 10 plus 1 is 11. When n equals 3, that's 5 times 3 plus 1. 15 plus 1 is 16, and so on. So these are the numbers in the set. Okay, I'm talking about 6, 11, 16. Those are numbers in the form, okay, in this set. The question is if we take any two numbers in here, multiply them together, is that number still in the set? So let's take just 6 and 11 just for fun. So is 6 times 11, all right, which is 66, in the set? That's the big question. So what we could do is we could, keep on going with this list and see if they're in the set. Okay, you could do that, and we will do that. All right, but just let me show you a little bit faster way to think about it. Mathematicians would say, well, okay, if this is in the set, that's basically asking you, is 66 in the form of, okay, in the form of this right here. Okay, let's put it in red, big mole. Here's your form right here. Is it in the form of 5n plus 1? Question mark. That's the same question. Is it in the set? So basically what I'm asking you, if you want to answer this question algebraically here, you'd say, well, if 66 is in the form, that means that 66 must be equal to 5n plus 1, where n is natural. N must be natural. N is a natural number. So let's solve for n and see if we get a natural number. If we do, it's in the set. If n is not natural, or if we solve for this and n is not natural, maybe it's a fraction or a decimal, then n is not natural, then this number 66 is not in the set. And I'll prove it to you here in a minute. But let's go ahead and solve for this. Okay, so let's subtract 1. So we get 65 equals 5n. Divide by 5. We're just doing algebra 1 here. All right. And then 65 divided by 5 is 13. Okay, and this is obviously natural. It's a natural number. Okay, what does that tell me? It tells me that 66 is in the set. It's the 13th number in the set. 66 is the 13th number in the set. So I just multiplied any two numbers in the set, the first two actually, 6 and 11. I got 66, and I showed that 66 is in the set by showing that n is natural. All right, it's the 13th number in the set. Now, if you guys do not believe me, well, then let's show it. Okay, so here we go. Let's prove it. Well, actually, let's show it first. Okay. All right, so let me get something going here. I need some more room. Okay, so let me just create some more room here. Oh, let me do a OneNote thing. I need to create some space. The new versions of OneNote, you don't have to do this, but I got to do what I got to do. Okay, so let's list the numbers in the set. Let's go to the 13th number. So list the numbers in the set. Here we go. So set I. Okay, so if we go back up here, the first number is 6, and then 11, then 16. First, second, third, right? Okay, we already did that work, so I don't have to show it again. So 6, 11, 16, and there's obviously a pattern. What's the pattern? Well, you simply add 5, all right? 6 plus 5 is 11. Plus 5 is 16, and that number, guess what? That number is seen in the form, okay? It's 5 times the natural plus 1 more. That's called the slope, actually, if you were going to be graphing all these, but that's okay. So to get the next view, simply add 5. There's your pattern. So I don't need to work it all out in detail like I did before and substitute the numbers in and do that 13 times. You just keep on adding 5 in the sequence. So 21, 26, 31, 36, 41. You just keep on adding 5. Okay, that's the pattern. Keep adding 5. So 46, 51, we got to go to the 13th one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is n equals 10. 5 times 10 plus 1 is 51. That's why that's the 10th number. Okay, so I got to go to the 13th. So add 5 is 56. Add 5 again, 61. Add 5 again, 66. So this is n equals 13. This is the 13th value. All right, boom, 13th number, and the list goes on and on. Okay, so this is one way to easily show algebraically that you have a number in the set. Okay, if it's of the form 5n plus 1, set it equal to 5n plus 1, and solve for n, and if n is natural, like you get a natural number, then the number's in the set. Now, if the number's in the set, then this suggests right here, all right, that the set is closed. So this is not a proof. This suggests, okay, that the set is closed under multiplication. The set is closed under the operation of multiplication. Okay, now this is not a proof, so we have to prove it. So what we do is we prove it. Okay, so here we go. Here's the proof. Okay, so what we did is explore right now. So if you take a look at what we've done so far, I just substituted some numbers in the form of 5n plus 1. I generated 6, 11, 16, and then I just picked two of them, multiplied them together, and I got 66, and I showed that it was in the set. And I showed again that it is actually in the set. I just listed them all out, and I showed that the 13th one is 66, which is obviously in the set. So this suggests that it's closed. It's not a proof. So you need a algebraic proof, okay, an algebraic style. Algebraic style proof, okay, using algebra. Okay, so here we go. So what you do is you say, we need to take two general numbers in the set. And remember the form, okay, the form is 5n plus 1. So we let a equal to 5n plus 1. That's your first number. A is their first one. B, it's got to be different. So you use a different variable. So 5m plus 1. Where n and m are natural numbers. You have to specify the type of numbers when you're in a proof. You have to be very specific. Okay, n and m are natural numbers. Okay, they're an element of this set right here. So now we have to show that a times b is in the set. Okay, so remember the form of the number. So the form that we're looking for is 5 times a natural plus 1. That's the form. 5 times a natural plus 1. I'm going to highlight that. We have to show that if we multiply a and b together, we get 5 times a natural plus 1. So here we go. So we say a times b, since we're showing that it's closed under multiplication, is equal to 5n plus 1 times 5 times m plus 1. You got to multiply them together and check or prove that the result is in the set. Okay, now with the way you multiply binomials, you can either use the FOIL method, okay, or distributive property, either one. Okay, so here we go. So this is equal to 5n times 5m is 25 nm. You multiply the constants, multiply the n and m. 5n times 1 is obviously 5n. And then here, you got to multiply the inner product. 1 times 5m is obviously 5m. And then 1 times 1 is 1. FOIL has 4 letters, right? Okay, from Algebra 1 back in the day, many, many years ago, okay, you multiply 4 times. Now, I see the plus 1 here, and notice the plus 1 here. So I got to show that all this stuff is in the form of 5 times the natural number. So simply factor out a 5 and just bring down the plus 1. So take a look at right here. So you see this plus 1, there's a plus 1, there's a plus 1. That is already in the form. So we just need to get the other part, the 5 times the natural. So if you factor out the 5, you get 5 times nm. Again, if you distribute back through mentally, you'll see that that works. 5 times 5 is 25. Factor out the 5 from the middle term, you get n. Factor out the 5 from the third term, you get m. And again, you check by distributing here. That's how you check it mentally. See that? Okay, but the question is this natural? So this part right here, is this natural? Is this natural? So let's talk about that for a second. This goes back to the previous activity on 1C1. So let's take a look at the first part. Get your eyes right here. A natural number 5 times a natural number times a natural. Is that natural? Well, the answer is yes, because we talked about that in the previous lesson. A natural times a natural is a natural. We said it was closed under multiplication. So then, okay, so now we know that this is natural, and this is natural. So is a natural plus a natural plus a natural a natural? And the answer is yes, because we showed it's closed under addition. That was from the previous activity. So the answer is yes. So this right here, this whole quantity, 5n plus 5nm plus n plus m, is natural. So this is 5 times the natural plus 1, natural number plus 1, all right, and therefore it's in the same form. Okay, this is the form of every number in the set. Form of every number in the set. Okay, and therefore it is closed. So set I is closed under multiplication. There we go. And that is my conclusion. That's a formal algebraic proof. Without skipping any steps, by the way. Okay, now this is a video, right? So you can always go back and listen to this again if you want to digest it some more. Okay, now not all sets of these crazy forms are closed, so don't assume that these sets are always closed under multiplication. If I change the number 5 to some other number, so you have to test it first, okay, and then check to see what's going on. Okay, so let me just go over one more thing here. So let's take a look at the second example, example 2. So consider this. I'm going to change it up a little bit because you need to see a variety. one example is typically not enough. So a set, I'm going to call it Z, just for funsies, right? So if this set Z, which is numbers of the form, this time I'm going to change it I'm going to change it to 4x plus 6, where n is natural. N is natural here, so there's your set Z. Here's the form. Let's highlight it just for funsies right here. There's your form. Is it natural? Okay, where n is natural. Is this set closed under multiplication? Now, the reason why I pose this one is because this is a little bit different, obviously. And it's important that you guys don't always assume that, when an instructor gives an example, that the next one is just like it. It may be different. But you got to go through the same thought process. So as we did in the first one here, what we did is explore. Okay, you explore, when I say that, you explore mathematically or numerically. You write the numbers down. Substitute 1 in, what do you get? Substitute 2 in, what do you get? Substitute 3 in, what do you get? So let's do it. So when n equals 1, this is 4 times 1 plus 6. 4 and 6 is 10. When n is 2, you get 4 times 2, which is 8, plus 6 more, 14. When n is 3, you get 4 times 3 plus 6, 12 and 6, 18, all right, etc. Okay. Now, if I take any two of these numbers in the set, here are the numbers in the set, 10, 14, 18, multiply them together, do I get a number in the set? All right, so the big question is 10 times 14, these two numbers here, all right, which is 140, is 140 in the set? So in the set, that's the big question. Now you can continue listing these out, but you're going to be doing this list for a long time. So basically what you need to do algebraically is you have to check is 140 of the form 4x plus 6, or 4n plus 6, where n is natural. Is n natural? If you solve it, that's the big question. So let's solve it. So subtract 6. I get 134 equals a 4n divided by 4. Again, this is just algebra 1 stuff here, guys. So does this result give you a natural number? Well, take 134 divided by 4. Divides 3 times, remainder 2. Remainder 1. And then 4 into 14, 3 times, remainder 2. That's what I was thinking ahead. So it's not natural. This is 33 and 2/4. So the result is 33 and 2/4. Okay, that's not natural. Not natural. Okay, what that tells me is that 140 is not in the set. 140 is not in the set. Okay, so this is your counterexample. Okay, so this is the counterexample. Okay, but now let's say you didn't do this algebraic method. Okay, so this is not closed. This tells me that, Z is not closed. Okay, under multiplication. Okay, but let's say that you try to prove it. So I'm going to try to prove that it's closed, and I'm going to end up with a contradiction. Okay, so try to prove. We already know it's not. Okay, look, I just wrote that down. So try to prove it, and we're going to show a contradiction. That means we're going to end up with a mathematical problem that doesn't allow us to prove it. Okay, and that's important that you guys know. Proof by contradiction is a mathematical proving technique. It's called proof by contradiction. You may have seen it in geometry, but it depends on your instructor and how detailed they got. Okay, so let's try to prove it just for funsies. All right, so let's take two numbers of the form. Remember, the form for this one is 4n plus 6. Okay, so 4 times the natural plus 6. So here we go. We're going to try to prove it, and we're going to show a contradiction. Okay, try to prove it. Show a contradiction. Contradiction. that means something that makes it false, okay? Which means you cannot prove this, all right? Because we said it's not close. So there's no way you can prove it, okay? So we have to show a contradiction. All right, so let A equal to 4n plus 6. Let B equal to something of the same form, but use a different variable. All right, and multiply them together and see what happens. Just like the previous one, right? You want to follow the same strategy. The way to get good at these type of proofs and thinking is to explore it mathematically and then do it algebraically and make sense out of it. So we have, let's multiply them together. So 16nm plus 24n plus 24m plus 36. Now remember the form. So let me put this in red. The form of any number in that set is 4 times the natural plus 6. That's your form. Okay, so I'm going to highlight that. I have to show that this is in the same form. And already I have a problem here because I got a plus 36 and not a plus 6. That's a problem. But I'm going to try to get this portion right here as 4 times the natural. That's going to be easy. I'm going to factor out the 4. 4 times 4nm is 16nm. 4 times 6n is 24m. Excuse me. And then 4 times 6m is 24m. And then I've got this 36 hanging around. So this right here, this is natural. So what I just showed that is in the form as 4 times the natural, all right, plus 36. The first part's good, but the second part is not, okay? This is not in the form of 4 times the natural plus 6. So because of this right here, the plus 6 and this is plus 36, right there, there's a problem, okay? Not in the form. Not in the form of 4 times the natural plus 6. Okay, and you can't prove it, so it's not closed. Okay, so there you go. So you could try to prove things when in doubt, but if you end up with a contradiction like this, that you have a problem here, you can't show that it's in the same form, well, guess what? It's not closed. Why? Because it's not closed. All right, we came up with a counterexample in the beginning. We took 10 and 14, we multiplied them together, got 140. And 140 is not in the form of 4n plus 6 because we got a fraction here, which is not natural, which tells you that 140 is not in the set. So there's your counterexample. It's not closed. Do you have to do this right here? Do you have to try to prove it? No. I just did that to make a point because I wanted to show that even if you tried to prove it, it's not possible to prove that it's closed. Why? Because it's not. Okay, it's not close. 140 is not in the set. Once you come up with a single counterexample, you are done, people. You don't have to prove it because it's not possible to prove because this is not closed under multiplication. All right, so you saw an example where we could prove closure, okay, in the first set example. And this one here, 5m plus 1, that is possible to prove closure under multiplication. And then I showed you another example right here where it is not possible to prove closure under multiplication. So don't assume in the beginning that it's either closed or not closed. You got to study it, you got to explore. I use the word explore. And when I say that, I mean write some numbers down, okay? Be mathematical, all right? Generate numbers in the set. Generate numbers in the set. That's what I mean by explore, okay? And if you do that, you're going to be able to see things. Mathematicians, I don't care how smart they are, they always explore and look at it, and they have these epiphanies, these aha moments where they look at the numbers generated and they go, oh, I get this, okay? So don't be afraid to write things down. In fact, the best mathematicians do. Okay, so this is just a couple examples on closure and proving algebraically, and it's a prep for 1C2. All right, and if you want to be successful, mathematically speaking, give this a shot, study it, practice it, and own it. Okay, and then obviously do 1C2, and we'll do some more work in the future. All right, this is Mr. Ainsworth. I'll see you in my next lesson. See ya, bye.